Calorimetry. Now, ice is at minus 20 degrees Celsius. We heat ice. Ice comes to at 0 degrees Celsius. Further we heat ice. It turns to water, changes its state. Water at 0 degrees Celsius. Further heat water. It turns to 100 degrees Celsius. When water is heated, it turns to steam at 100 degrees Celsius. And then temperature of steam rises. Say it rises to 120 degrees Celsius. Now the first part of the chapter deals with where there is a change in temperature. At this point, when ice changes from minus 20 to 0, when ice changes from minus 20 to 0, here there is a change in temperature. Again, when the temperature of water changes from 0 to 100, here there is a change in temperature. Again, when the temperature of steam rises from 100 to 120, the other part where ice changes from ice at 0 to water at 0, here there is a change of state. Water at 100 to steam at 100, again here there is a change of state. Now first part of the chapter deals with the change in temperature. Now whenever there is a change in temperature, either heat is lost or heat is gained. So whenever there is a change in temperature, whenever there is a change in temperature, either heat is lost or heat is gained. Now in this case, heat if we denote by the letter Q, the heat lost or heat gained, Q, is equal to the mass of the body peak heat capacity of the body into change in temperature. Let the change in temperature be represented by the letter theta. So the heat lost or heat gained is mass of the body into specific heat capacity of the body into change in temperature. Now, to study this, Q equal to M into C into theta, we have to have a clear idea of this term specific heat capacity. We know what is mass, we know what is change in temperature. We have to have a clear idea of what is specific heat capacity of a substance. Now we have the formula Q equal to M into C into theta. Now if M is equal to 1 kg or 1 gram, if theta equal to 1 degree Celsius rise or 1 Kelvin rise or fall, it may rise or it may fall, then Q is equal to mass is 1, theta is 1. In this case, from this expression we see C is equal to Q. So specific heat capacity C can be defined as Q, as a heat. Specific heat capacity can be defined as the amount of heat energy required. Specific heat capacity of a substance can be defined as specific heat capacity of a substance is the amount of heat energy. It is the amount of heat energy required to raise the temperature of unit mass of that substance. Through 1 degree Celsius or 1 Kelvin. Now when we write the definition of specific heat capacity, here we write as unit mass. It is not necessary to mention whether it is 1 kg or 1 gram. But when we write about the change in temperature, it is very important that we write 1 degree Celsius or 1 Kelvin, because 1 degree Fahrenheit will be wrong. So for temperature, it is very important that we write theta as 1 degree Celsius rise or fall or 1 Kelvin. For mass, unit mass is enough. It is the amount of heat. C is equal to Q. C is equal to Q. When mass is 1 and rise in temperature is 1 degree Celsius or 1 Kelvin. Now what is the unit of specific heat capacity? C from here is Q by M into theta. Now Q is in joule, mass is in kg or gram, theta is rise in temperature either in Celsius or Kelvin. So here we have Kelvin. So unit of C will be joule per kg per Kelvin. This is the SI unit of specific heat capacity, joule per kg per Kelvin. At times, instead of specific heat capacity, heat capacity is given. Now what is this heat capacity? Heat capacity is the product of mass and specific heat capacity. Now we have Q equal to M into C into theta. This M into C is called heat capacity. So, how do you define this heat capacity? If theta equal to 1 degree Celsius or 1 Kelvin, if theta is equal to 1 degree Celsius or 1 Kelvin, then Q equal to heat capacity. So what is the difference between specific heat capacity and heat capacity? Say this is a mass m. From here, if you take unit mass 1 kg, then the heat required to raise this mass by 1 degree Celsius is specific heat capacity. And the heat required to raise the full mass through 1 degree Celsius, heat required to raise the full mass through 1 degree Celsius is heat capacity. Once again, from this big mass, if we cut out a 1 kg mass or 1 gram mass, and the heat needed to change its temperature by 1 degree Celsius is specific heat capacity. And the heat required to raise the full mass, full body, by 1 degree Celsius is my heat capacity. So heat capacity is the amount of heat energy required to raise the temperature of the full body by 1 degree Celsius. Now what is the unit of heat capacity? Q equal to m into C into theta. Heat capacity is m into C. So this m into C is Q by theta. Q has the unit joule, theta has degree Celsius or Kelvin. So unit of heat capacity will be joule per Kelvin. Heat capacity is also known as thermal capacity. Thermal capacity is an alternative word for heat capacity. Now to study this chapter, we have to know the detailed structure of a calorimeter. A calorimeter is used to study the chapter calorimetry. Now first let us look into the structure of a calorimeter. Now this is a calorimeter. The inner wall is made of Now, a calorimeter is more or less like a thermoflask. Now, this is a wooden jacket. This is a polished copper beaker. This is a wooden lid. This is a wooden lid which has two holes. Through one hole, we have a thermometer. Through one hole, we have a thermometer inserted. This is a thermometer. And through the other hole, we have a stirrer inserted. This is a thermometer. And this is a stirrer. Now this calorimeter is exactly like a thermoflask. Now inside this we have an insulating material. This is an insulating material, say for example wool. Now this copper beaker is highly polished. Why is it polished? This is polished to reduce heat loss by radiation. Polished surfaces do not radiate heat. So this is polished to reduce heat loss by radiation. Actually, the outer and inner surfaces of the vessel are polished to reduce heat loss by radiation. The outer and inner surfaces of the vessel are polished to reduce heat loss by radiation. Now this wooden jacket and this insulating material, both of them together reduce heat loss by conduction. They reduce heat loss by conduction. So this wooden jacket and the insulating material reduce heat loss by the method of conduction. The wooden lid on top. Convection always occur upward. Wooden lid on top prevents heat loss by convection. Thermometer measures the temperature. Stirrer is used for fast uniform mixing. So in a calorimeter, heat loss is prevented by conduction, by convection, and by radiation. Now this calorimeter is used to measure the specific heat capacity of a substance. Say we take a mass M whose specific heat capacity we have to find out. It is very hot. The temperature of this body is say theta 2 degrees Celsius. It is hot. Say we take water inside the calorimeter. Mass of water taken is M1. Specific heat capacity of water is 4200 joule per kg per Kelvin, or if you convert it into gram, it is 4.2 joule per gram per Kelvin. That means to heat 1 gram of water by 1 degree Celsius, we need 4.2 joule. Or to heat 1 kg of water by 1 degree Celsius, we need 4200 joule. Say the initial temperature of water is theta 1 degrees Celsius. Now, mass of this calorimeter is M2. Specific heat capacity of copper is say 0.4, it is very small, joule per gram per Kelvin. Now this water is at theta 1 degrees Celsius. So the vessel will also be at theta 1 degrees Celsius. So initial temperature of calorimeter is theta 1 degrees Celsius. The temperature of the calorimeter and its contents is the same. Now we have to find out the specific heat capacity of this body. Now what we do? We open the lid and gently place this mass inside this water without water being splashed out, because we have taken the mass of water as M1. If water splashes out, then the mass will decrease. Now as soon as M is put inside the water, the lid is again placed in the proper position so that no heat is lost from the calorimeter to the surroundings. As no heat is lost from the principle of mixtures or the principle of calorimetry, we have that the heat which the body loses, the principle tells us that if the system is fully insulated, if the system is fully insulated, there is no loss of heat, then heat lost by the body was hot, the body will lose heat. The heat lost by the body is equal to heat gained by water plus calorimeter. The body loses heat. The body was hot. The body loses heat. And the water and the calorimeter gains heat. And let the final temperature of all the components be theta degree Celsius. Let the final temperature be theta degree Celsius. Now we have studied that whenever there is a change in temperature, the heat lost or gained is m into c into theta, mass of the body into specific heat capacity of the body into change in temperature. So we come back to the diagram. The body loses heat, the water and the calorimeter gains heat, and the formula is mc theta. Heat lost by the body, mass of the body was m, specific heat capacity of the body was c. Body was at theta 2 degrees Celsius and the final temperature is theta. So this is the change in temperature of the body. This is the change in temperature of the body. This is equal to heat gained by water. Water had mass m1, specific heat capacity in CGS is 4.2. Water was at theta 1 degree Celsius. Its temperature rises to theta. Here theta is greater than theta 1 plus calorimeter has mass m2. It is made up of copper. In CGS, its specific heat capacity is 0.4. Calorimeter was at theta 1. Final temperature was theta. So this is the change in temperature of calorimeter. So with this expression, we can find out C. Now at times, this calorimeter is not mentioned in the numerical. In that case, this can be ignored as this value is very, very small. At times, when the calorimeter is not mentioned in the sum, then we can ignore the heat taken by the calorimeter. Actually, the principle of mixtures is nothing but the law of conservation of energy. This question is very, very important. The principle of mixtures is based on which law? It is based on the law of conservation of energy. This question is very, very important. Now, from here, we can get explain why questions. Say, let us take a question. Hot water bottles are used for fermentation. Why? We use hot water bags for fermentation. Now the keywords for this answer is water has high specific heat capacity. Specific heat capacity, what was it? It was the heat required to change unit mass by 1 degree Celsius. Now specific heat capacity of water is 4200 joule per kg per Kelvin. That means to heat 1 kg water, just by 1 degree Celsius, we need 4200 joule of heat energy. That means water, when we heat water just by 1 degree Celsius, we need 4200 joule of energy. Water has a high specific heat capacity. That means to cool just by 1 degree Celsius, it has to liberate this 4200 joule of energy. So water does not cool quickly. It has to liberate a lot of energy to cool. It has to liberate this amount of energy just to cool by 1 degree Celsius. So it will not cool quickly due to its large specific heat capacity, and hence it will provide heat energy for fermentation, provides heat energy for fermentation for a longer period of time. So the keywords here is water has high specific heat capacity. This is one keyword. Does not cool quickly, provides heat for a longer period of time. High specific heat capacity, does not cool quickly, provides heat for a longer period of time. You have to write the answer with the keywords. Let us go to the second question from this. Explain why. Say, you get a question. Water is used as an effective coolant. Why? Water is used as an effective coolant. Why? Now the keywords for here again will be, one is the high specific heat capacity of water. Water has high specific heat capacity. This is one keyword. Now, when water is allowed to flow in pipes in the heated part of the machine, heat energy is being removed. So, water extracts more heat from the surroundings. Water extracts more heat from the surroundings. Water extracts more heat from the surroundings without its temperature rising much, because it will take 4200 joule of energy just to rise by 1 degree Celsius. Now when something cools some other thing, then if that substance get heated up, you have to add something else to cool it. Now this is the advantage of water, is it extracts more heat from the surroundings without much rise in its temperature. Without much rise in its temperature. This is very, very important. So what are the keywords? High specific heat capacity of water, extracts more heat without much rise. These three words should be there. Water has high specific heat capacity, extracts more heat from the surroundings without much rise in its temperature. So these type of questions should be answered with the keywords only. Now a very, very common question which comes in calorimetry is, why is a calorimeter, now why is a calorimeter made of now here you can get two type of question. Why is a calorimeter made of copper, or why is a calorimeter made of thin sheet of copper? Now two answers will be slightly different. Now when the question is why is it made of thin sheet of copper, now Q is M into C into theta. When we talk about thin, that means mass is less, and C of copper is also less. So product of M and C which is thermal capacity, is less. So in this case, we have to write specific heat capacity of copper is low, and making it thin, mass is less, and hence thermal capacity is low. So you have to write C is low. Since it is thin, mass is less, and the product M into C is less. That means we have to write that the thermal capacity is low. That is the key word here. Here we are going to write thermal capacity becomes low. So it takes negligible amount of heat from its contents to attain the final temperature. So here the keywords will be C low, mass low, thermal capacity low, takes negligible heat to attain its temperature. But if the question is why the calorimeter is made of copper, the thin word is missing. In that case, the mass will not be taken into account. The mass will not be taken into account since it is not mentioned that it is thin. In that case, we have to write copper is a good conductor of heat. Copper is a good conductor of heat. You can add this to the second thin sheet of copper. Copper is a good conductor of heat, so the vessel acquires the temperature of its contents fast. So the vessel acquires the temperature of its contents fast. And secondly, you can add, since it's copper, its specific heat capacity is low. Specific heat capacity is low. The C is low. So the calorimeter takes a negligible amount of heat to acquire the temperature. So this can be added. So it takes negligible amount of heat to attain its temperature. You can add the first point to the thin sheet of copper, but this massless cannot be used for if you are asked why is a calorimeter made of copper. If the question is thin sheet of copper, then only you add that the mass is less, thermal capacity is low. We cannot use thermal capacity for the question only copper is there. For the question where only copper is there, thermal capacity is the wrong keyword. Or we can get a question like this. Why is the base of an electric iron made thick and heavy? Now the keywords for here is for thick you have greater mass, thick and heavy. So Q equal to M into C into theta. This mass is more. If mass is more, then product of M into C is more. So we can say that by making it thick and heavy, thermal capacity of the base of the electric iron becomes large. Thermal capacity of the base of the electric iron becomes large. This is one keyword. Thermal capacity becomes large. And the second keyword will be remains hot. The electric iron remains hot for a long duration. Remains hot for a long duration even after switching off the current. Even after switching off the current. Even after switching off is important because the electric iron has to remain hot for a long time. So we make the base heavy. The mass is more. Thermal capacity is M into C. Thermal capacity is M into C. So if mass is more, thermal capacity is more. So the heat retained by it is more. So it remains hot for a long duration of time. Even when you switch off the current, you can use the electric iron for a long period of time. Now, numericals based on this first part, where there is a change in temperature. Let me take a sum. Say we take a question. 1 kg of water 1 kg of water is contained in a 1.25 kilowatt kettle. Calculate the time taken for the temperature of water to rise from 25 degrees Celsius to 100 degrees Celsius. Now the question is, we have to calculate the time taken for water to rise from 25 to 100. Now it is given that specific heat capacity of water is 4.2 joule per gram per Kelvin. Now the formula for Q is m into C into theta. Mass is 1 kg. So mass is 1 kg. C is given in gram. We have to convert it into kg. 4200 joule per kg per Kelvin. From gram to per Kelvin, we have to multiply with 1000. So C is 4200 joule per kg per Kelvin. And rise in temperature is 100 minus 25 Kelvin. Kg cancels, Kelvin cancels. So the heat is 4200 into 75 joule. This much of heat is required. Power of the kettle is 1.25 kilowatt. I have to calculate the time. Now power is heat by time, work by time. Power is 1.25 kilowatt. I have to multiply it with 1000. 1250 watt. Heat is 4200 into 75. This much of heat is required. Now I have to calculate the time. Power is heat by time. Now if time is calculated from here, from this expression, the time will come out to be 4 minutes and 12 seconds. If time is calculated, it will be 4 minutes and 12 seconds. Now let us take another sum. From the first part of the chapter, where there is a change in temperature. Say I take a question. The temperature of 600 gram of cold water rises by 15 degrees Celsius when 300 gram of hot water at 50 degrees Celsius is added to it. What was the initial temperature of cold water? Now the question is 600 gram of cold water was taken and 300 gram of hot water was taken. 600 gram of cold water rises, this word is very important, rises by 15 and the hot water was at 50. What was the initial temperature of cold water? Now let us take the final temperature as theta. Let the final temperature, let me take it as x. Let me take the final temperature as x. Now here we have to write, we know from the principle of calorimetry, you have to write the full calorimetry principle. If the system is properly insulated, full thing we have to write, and then heat lost by hot water is equal to heat gained by cold water. Now hot water mass is 300 gram. Specific heat is 4.2. Hot water was at initial temperature 50, final temperature is x. Cold water mass is 600 gram. Specific heat capacity is 4.2 and cold water rises by 15. Cold water rises by 15. So we cancel 4.2 from both the sides. 300 and 600 is 2. So 50 minus x is 30. So x is equal to 20 degrees Celsius. Now cold water rises by 15 degrees Celsius. And becomes 20 degrees Celsius. It rises by 15 and then comes to 20. So what is the initial temperature? The question is, what was the initial temperature of cold water? Definitely it is 20 minus 15. 5 degrees Celsius is the answer. Because if it was at 5 degrees Celsius, it rises by 15. It rises by 15 degrees Celsius. So the final temperature becomes 20 degrees Celsius. So if the final temperature is 20, which we have got, so initial temperature would have been 5. So in this way, we can solve the numericals of the first part of the chapter.